Today we will talk about topic of a calibration procedure for a digital instrument for electric power quality measurement. Writing by Alessandro Ferrero, Massimo Lazzaroni, Simona Saricone. This presentation is a part of electrical measurement and instrument present by Mr. ขวัญพงษ์บุรณดิษฐ์ and Mr. ศักมลคำพานิช
Abstract: The measurement of power quality is becoming an inspiring need in a deregulation electricity market where the source, producing, distribution, and distribution are steadily increasing in number and power. The instruments for power quality measurement are based on complex digital processing of the input signal, whose waveforms are highly variable. The calibration of the kind of instrument is therefore an open topic, especially when the uncertainty propagation towards the digital signal processing algorithm is concerned. This paper proposed an innovative product based on the Monte Carlo method, starting from the determination of the probability density function of the uncertainty contribution of every device from the signal input state to the analog to digital conversion state. This procedure estimates the probability density function of the measurement result and the measurement standard uncertainty as the standard deviation associated with this function. The result of the experimental work done on a prototype of a power quality measurement instrument is reported.
Introduction. The wide space of power electronic device from household appliance to industrial application in increasing the distortion on current and voltage in the electric power system to levels that are no longer negligible and is responsible for decreasing the electric power quality. Although the International Standard Organization has already inserted several recommendations on how to limit the injection of disturbance, and several methods and instruments have been proposed for power quality measurement, very few indications are given on how to estimate the measurement uncertainty of the proposed instrument. Several well-known methods are available in the literature for the estimation of the uncertainty of the signal conditional state and analog to digital conversion state of an instrument based on digital signal processing technique. However, the way the uncertainty affecting the input signal sample after the analog to digital conversion propagate through the DSP algorithm and affect the final measurement result has not yet been converted totally, thought a few attempts have been proposed. This paper presents a practical application of this procedure to an instrument for power quality measurement.
Method fundamental. The basic structure of an instrument for power quality measurement is shown in Fig 1. The current and voltage transducer have the twofold function of adapting the input signal dynamic to that of the AD input state and ensuring the necessary insulation between the electric system and the instrument. The traditional current and potential transformer do not feature the required accuracy on the frequency band required for power quality measurement.
Experimental result. Fig 2 show the experimental setup employed for the evaluation of the uncertainty contribution given by the gain and time delay error of the current transducer, and Fig 3 show the experimental setup employed for the evaluation of the same contribution given by the voltage transducer.
Fig 4 show the experimental setup employed for the calibration of the DAD conversion board. This board is based on a 12-bit ADC with simultaneous sampling on 8 channels and 500 kHz maximum sampling rate on a single channel. The calibrator outputs wave the voltage input length of the AD converter.
Fig 5 show the relative frequency histogram of the measured gain of one channel of the voltage transducer. The standard uncertainty of the gain evaluated as the standard deviation of the measured gain value is 9.5 multiplied 10 to minus 6.
Fig 9 show one element of the set of generate signal which correspond to the typical voltage and current waveform of the low voltage network on which power quality measurement have been performed. The fundamental frequency of this signal is 50 Hz and a sampling rate of 12.8 kHz over an observation interval of 4 periods was simulated, so that all subsequent computation have been performed on a sample window. Fig 10 show the relative frequency histogram of the evaluated voltage RMS value. The relative standard uncertainty is 0.04%. A similar histogram was obtained for the current RMS value with a relative standard uncertainty of 0.054%. When the harmonic components of current are considered, the relative standard uncertainty become 0.15%.
Conclusion: A calibration method has been proposed to estimate the measurement uncertainty of a DSP-based instrument and apply it to the calibration of an instrument for electric power quality measurement, thus solving an open problem. An automatic procedure was used to evaluate the contribution to the measurement uncertainty of the input transducer and the ADC system, and to estimate how they are distributed over their range. The final measurement uncertainty was then estimated by propagating that obtained distribution through the measurement algorithm.